So our next lesson, we're going to learn about titration curves. Titration curves are graphs of pH versus volume of titrant. Titrant is the chemical that is in the burette. So let's say instead of using an indicator to detect the equivalence point, you monitor the pH during the titration using a pH meter, an electronic device that measures pH of a solution. So what changes would be observed during the titration in terms of the pH? We're going to see what happens exactly on these graphs, and what happens to the pH depends on what the acid and base are that are involved in the titration. So let's take a look at our first example, and titration between a strong acid and a strong base. So it says strong acid with a strong base. So this is the chemical that we're starting off with in the flask, and this is what is in the burette. So let's go ahead and set up our axes. So we have pH on this axis, volume of base. So we're adding a base to an acid. So let's start off with initially after, or sorry, not after, but before we add any base. Let's say we have a 0.1 molar solution of HCl that we're titrating with 0.1 molar sodium hydroxide. What is the pH of the solution before any base has been added? Go ahead and calculate that value. So if you have 0.1 molar HCl, the concentration of H plus in that solution is 0.1. A negative log of 0.1 is 1. So the pH would be there before any base is added. Now, how about this? As you add sodium hydroxide, what is going to happen to the pH of the solution? Well, since we're adding a base, the pH is going to go up. But keep this in mind. As we're titrating initially in the very beginning, we have a lot more acid in the flask than we have base. And so, yeah, the pH is going to go up, but it's going to go up pretty steadily and pretty slowly. You reach a point, though, where even the addition of a very, very, very small amount of base causes the pH to shoot up several values on the pH scale. So this is nearly vertical. So if we look at from here to here, so the amount of the base that is added is very small, but the pH jumps up quite a bit. So let me get rid of my dotted lines here. So that's important to see. If we continue to add base, then the pH will kind of level off and we'll be left with something like this. Now, about halfway up this almost vertical part of the graph represents the equivalence point. So at the equivalence points, the base has completely neutralized the acid. Now, what is the pH at the equivalence point? Well, in the titration between hydrochloric acid and sodium hydroxide, the pH is going to be 7 at the equivalence point. Our solution, which contains sodium chloride, is a neutral salt. It's called neutral because its pH is 7. So this is a typical profile for titration curve, taking an acid, a strong acid, and titrating it with a strong base. How about the other way around? Actually, no, I don't know if I want to do this one yet. Let's go with, I think this is a typo. Actually, that's fine. We'll do this one. No, I'm going to skip ahead. Let's skip so we can stay consistent here. Let's go backwards. Take a strong base, so this is what is in the flask, and titrate that with a strong acid. This is what is in the burette. Let's say we have 0.1 molar sodium hydroxide that we're titrating with 0.1 molar HCl. All right, let's set up our axes, pH there, volume of acid or HCl there. Go ahead and calculate the pH of the solution before any acid has been added. Go ahead and pause and do that now, please. All right, so what did you get? The OH minus concentration of that solution is 0.1. If we negative log that, we get 1, which is the POH. Subtract that from 14, and that'll give us the pH, which is 13. So what do you think is going to happen to the pH as we add acid? Well, because we're adding acid, the pH is going to decrease slowly at first, and then we're going to see a sharp decrease, a drastic decrease in pH as we approach the equivalence point. And then as we continue to add more acid, the pH will then level off. So right here, again, about halfway up or halfway down that vertical part represents the equivalence point. And for the titration between a strong base and a strong acid, the pH at the equivalence point is 7. So that's typical profiles for strong acid, strong base titrations, and pH at the equivalence point in either case will be 7. All right, now let's go back to this one. Let's take a weak acid. Let's say we have 0.1 molar acetic acid. And we're going to titrate that with 0.1 molar sodium hydroxide. Acetic acid has a Ka of 1.8 times 10 to the negative fifth. So same as last time. Go ahead and calculate the pH of the solution before any base has been added. 0.1 molar acetic acid that has a Ka of 1.8 times 10 to the negative fifth. Go ahead and pause and do that now. X squared over 0.1 minus x equals Ka. Simplify, solve for x, negative log that, we get a little less than 3. 2.87, I believe, is the pH of the solution before any base has been added. So notice, same concentration as the HCl, 0.1 molar, but the pH is much higher because acetic acid is a weak acid. So what's going to happen to the pH as you add sodium hydroxide? So pH again is going to go up slowly at first. I should not level that off. Let me take that back. There we go. Let's try this again. So it goes up slowly at first, and then we reach a point where the pH shoots up a lot, and then once again we are leveling out once we have passed the equivalence point. So once again, right here, we have completely neutralized all of the acid with the sodium hydroxide. Interestingly enough, this region right here, the solution behaves as a buffer. So as we're titrating, the acetic acid is reacting, but that reaction is producing acetate. So if we look at the balance equation for the reaction between sodium hydroxide and acetic acid, we get water and sodium acetate. Acetate, of course, being the conjugate base of acetic acid. So this reaction is going to be using up some of this. It's going to be producing some of this. We're still going to have acetic acid in solution. We're going to have acetate in solution. Therefore, this is a buffer. And notice as you add base, the pH goes up by just a little bit. Now, interestingly enough here as well, what do you notice? That's the equivalence point of this titration, and this is true of any titration like this, titrating a weak acid with a strong base, the pH at the equivalence point will be greater than 7. Now I've exaggerated this, it's probably 8 point something, but I believe you get the points. pH at the equivalence point is greater than 7. Why is that? Well, you have at the equivalence point only sodium acetate. Sodium acetate is not a neutral salt. It's something called a basic salt. And it's called a basic salt because its solution has a pH of greater than 7. All right, we have one more. Let's say we have a weak base, so that's the chemical in the flask, and we titrate that with a strong acid. So let's say we have 0.1 molar aqueous ammonia, and we're titrating that with 0.1 molar hydrochloric acid. All right, set up our axes once again. And same as before, what is the pH of this solution before any acid has been added? We have 0.1 molar ammonia, which is a weak base. Ammonia has a Kb of 1.8 times 10 to the negative fifth. Now you may recognize that number happens to be the same number as the Ka of acetic acid, so that may help you with your calculation. So go ahead and pause the video and calculate the pH of the solution before any acid has been added. All right, so again, we want pH, not pOH, so we get about 11. So again, remember that's the pH of the 0.1 molar sodium hydroxide in the other example had a pH of 13. Same concentration as that, but this is a weak base compared to sodium hydroxide, which is a strong base, so the pH is lower. So what's going to happen to the pH as you add acid? Well, the pH is going to decrease. It has this kind of dip at the beginning here, and then decreases slowly, drastic decrease, and then kind of levels off. And I'm going to redraw this line because I don't know what's going on here with my pen. So let's try that again. That doesn't want to let me. All right, so let's try that again. pH goes down slowly, big drop, and then levels off. So again, right here represents the equivalence point. So let's take a look at the equation for this reaction. Reaction between ammonia and hydrochloric acid produces ammonium chloride. And what do you notice? pH at the equivalence point this time is less than 7. So this substance here, ammonium chloride, again, is not a neutral salt. It is an acidic salt. Why is it considered an acidic salt? Well, because a solution of that substance has a pH of less than 7. So again, typical profile for this type of titration, weak base with a strong acid. Again, what's important to see here is that the pH at the equivalence point is less than 7. All right, that concludes this lesson. Thank you for watching.